you guys picked up a classroom copy. You're not going to write in this classroom copy, but if you can just take notes on a separate sheet. And our calendar is the same as the previous one, so I didn't print out a new calendar here, but we're going to do linear approximation today. We'll do related rates. Related rates is going to be the bulk of this unit. And then we'll do indeterminate form, L'Hopital's rule. These are smaller topics here. And then we'll start quiz review next Wednesday, Thursday. And then I want to give us a bit more time for practice, but I also want to start the next unit. So I think our quiz will be next, sorry, not next week, but the week after, Tuesday after. So we'll have new notes on Friday and Monday, but then we can also build in some practice into that. And then the Tuesday after next will be our quiz. And by then I'll give you a new calendar. Okay, so today 4.2 linear approximation. So we have these shapes that we'll talk about later, but I think you know what this is here. This is concave up. So concave up, it's like a parabola that opens up, has a U shape that's right side up, and then you have something that's concave down. Next unit we'll talk about how to find or when a graph is going to be experiencing concave down, but it's going to be curvature. Looks like an upside down U. It's a parabola that opens down. And let's talk first about tangent line. So tangent line, we know we can build tangent line equation. We just have to find the order pair, find the slope from the derivative, and then we can create that tangent line equation. So let's say we have a tangent line that is off of a concave up graph. So I'll just pick up a random point here. Now, what we're going to do today is we're going to be creating the tangent line equation, and then we're going to ask the tangent line to tell us a value that will approximate the value on the curve. And obviously, it's going to be not the same, because if I pick let's say the tangent was at x equals 4. We know that the tangent line and the curve will share the same y value at 4. But if it's 4.1, is 4.1 going to be the same y value on the curve versus the line? They're not, right? But it's going to be pretty close. And so that's enough for us to do an approximation. We're going to use the tangent line to approximate values of the curve that's relatively close to that tangent line. Relatively close to that point of tangency. So you can imagine, right, a point that is 4.1 on the graph will give you this point, but then 4.1 on the curve will give you this point. And the thing I want to highlight is that anytime you have a graph that's concave up, no matter where that tangent line is, and if you want to do any approximation with that tangent line, is that approximation going to be above or below the actual value? Is the tangent line approximation going to be below or above the curve's value? Below. Okay, so that's really the big takeaway here, is that no matter where your tangent line is, as long as the graph is concave up, any tangent line is going to sit below the curve. And if it sits below the curve, any point on that tangent line will underestimate your function value. Okay, so tangent line will underestimate function value if my graph is concave up. That's really the big takeaway that I want us to have initially. And this is not something you have to memorize, because if you just draw a concave up graph and do a tangent line, you should be able to visually see, okay, this tangent line is always going to sit below the curve. And you don't have to prove it at all, except to just kind of state it. same idea, right? If I have a graph that's concave down, then any tangent line that skims the surface of that concave down graph is always going to sit above. So therefore, your tangent line is going to overestimate the actual point on the curve. All right, does that make sense? So no need to memorize. If you just draw a parabola opening up or down, you can visually see whether your line is sitting above the graph or is it sitting below the curve. So this, I know this sounds intimidating, like we're doing linear approximation, but it really is just these two things added together. So we're going to build our line. Okay? So we're going to build our tangent line. We know how to do that. We'll take our order pair. We'll take our slope from the derivative, point slope form. And then all we're doing after that is we're just going to plug in the decimal value they give us. Okay? So really just as easy as one step beyond your tangent line equation. Okay? We already know tangent line equation. The additional step is just plugging that decimal value in, and that's it. Okay, it really is as easy as that. The bulk of the work is something that you already know how to do, which is just building that tangent line. Once you get that tangent line equation up and running, then it's easy. Then just plug the decimal value in. Right? And again, you'll get to use your calculator in this unit. All right, so number one. F is concave up, so my graph is concave up on the domain. So we know our graph is going to look like this. And we have information about the order pair and slope. F of 4 equals 5, F prime of 4 equals 3. What is the estimate for F of 3.8 using a local linear approximation? So we don't worry about that 3.8 at the beginning. We're just going to build our tangent line equation. So we have our order pair. We have our slope. And then we just put that tangent line equation into point slope form. All right, this is easy, right? We've been doing this ever since we started derivative unit. There is one thing though that we need to do is to just get that y by itself. So so I guess we do have one additional step, and that is just to get that y by itself. But you don't have to worry about combining any terms after that. Just move that +5 over. Okay. So if you can get your equation into this form, then we just plug that 3.8 in, and then we're done. That's all we're doing. Just plug that 3.8 in, and then we have our approximation. So we say y of 3.8 is equal to 3 times 3.8 minus 4 plus 5, which is equal to 4.4. Now, on the quiz, if you want to get to 4.4, that's fine. But also to let you know, on the AP exam, if this was not a calculator, you can leave your answer in this form, and they will not take off any points at all. Okay. Any messiness you give, in fact, on the AP exam, it's a good strategy to leave your answer unsimplified. As messy as it looks, it does two things for you. It saves you time, and second, it prevents potential mistakes after. Right. So if you make a careless mistake after in the simplifying process, you would get points. You'll get dinged for your miscalculation. But if you leave your answer unsimplified and it's the correct version of the answer, then they'll give you full credit there. Yeah.
Does that mean? But they'll ask us sometimes to simplify it. Right?
Possibly, if it's multiple choice, you may have to get it down to this to match the answer choice.
Will you accept that answer?
Yeah, I'll accept this as well. Yeah,
Sweet.
But on the AP exam, if you sometimes you may have to simplify to get down to the match their answer. But then if it's free response, no calculator, they'll have to accept something that is in this form. Right. So we know that the graph is concave up, and we're just building some tangent line on that concave up graph. Is this an under or overestimate? Is that 4.4 going to be higher or lower than the actual value on the curve? It's going to be lower, right? We don't know what the actual value is. We don't have enough data, but we definitely know based off of this concave up and linear approximation, it's going to be some lower value. We don't even have to know how much lower it is. We don't even have to know the accuracy of our approximation. We just have to state that since f of x is concave up, our linear approximation will produce an under approximation. So the only reasoning we have to provide is the fact that the graph is concave up. Okay, you guys want to try number 2? So number 2, you have to do a little bit more work because you have to actually find the derivative before you can find the slope, but we know how to do that, just power rule. So find your order pair from the function, build your derivative, plug in, find your slope from your derivative, point slope form, solve for y, and then once you have solved for y, then plug in your decimal, and then can you determine if that approximation that you found is an over or under approximation? Okay, so try that. Use the process that we did for number 1 to help you as you work through 2. Okay, so I found the order pair first. I plugged 1 into the function, and I got f of 1 is equal to 1. Next up, I found the derivative. Power rule, 5x becomes 5, minus 2x cubed becomes minus 6x squared. Plug 1 into the derivative to get my slope. Once I have my order pair and my slope, point slope form. Any questions here? Just a slight adjustment here, just to get that y by itself, I added 1 to the right side. So y equals -1, x minus 1 plus 1. I'm just getting you ready for linear approximation here. Plug 1.1 in for x, and then we're done. We have our decimal value. Again, if you leave your answer unsimplified, I'll be okay with it. But if you simplify it, it'll be 0.9. Okay, our graph is concave down. So any linear approximation is going to be what? Overestimation, yeah. That's all we need to state.
Is that all we would have to say on a test?
Yeah, that's all you need to say, yeah. Now, later on, we're going to have a strategy where we can determine if the graph is concave down, but we haven't learned that yet. Okay, but ultimately, once you can confirm this information, either where they give it to you or you find that out on your own, that's enough for your justification.
There's any chance not be true.
I'm sorry?
You say there's a chance.
No, I'm just saying that, that right now, you're told that the graph is concave down. Later on, we're gonna be able to determine on our own whether the
Oh.
graph is concave down or concave up. But the reasoning is still gonna be the same. Okay, any questions? Okay, so, sometimes I think, students run into a little bit of trouble into this problem because they see that decimal value and they just want to start working with that number, but you just have to keep reminding yourself, okay, this is the last step. You're going to focus your attention on building that tangent line in the equation first, get your point, get your slope, build that tangent line, and then that decimal value will play a role at the very end. Okay, so your decimal value is not going to be the first thing you do. It's going to be the last thing that you do. So I see students, they start involving that decimal value at the beginning of the problem, and then that just throws them off. Okay, number three. Number three says, consider the differential equation dy dx equals e to the y times 2x squared minus 5x. I know this sounds complicated. Differential equation, what is that? That's just a derivative formula, right? It's like this f prime. It's like this f prime of x equals 5 minus 6x squared. It does the same thing. You give it information, in return it gets you slope. It just looks more complicated because it may have y's and x's in it. Okay, but it's the same idea. You give it information, it'll give you the slope. It's just a derivative equation. But a lot of times we call it a differential equation when it's a little bit more complicated, when there's y's involved. But all it means is that it just needs additional information besides x to get you to your slope. Okay, so let me walk through number three with you. Consider differential equation, another word, a slope formula. Let y equals f of x be the particular solution. The initial condition, f of 2 equals 0. Write the equation for the tangent line at 2, 0. So this one is kind of walking through each step of the way. Sometimes the problem was just say, find the linear approximation at f of 2.2, and we're just going to have to know that we have to build a tangent line before we can get to that f of 2.2. So all we need is the order pair and slope. So the order pair, that's provided for you. The slope, because it's x and y, we do vertical line 2, 0 to indicate that we're about to plug in both the x and the y value into the derivative. And I'm just going to go down the line here, replace the x's with 2's and replace the y's with 0. Anything raised to the 0 power is what? Is 1, right? So e to the 0 is 1. 2 squared is 4, 4 times 2 is 8, 8 minus 10 is negative 2. Negative 2 times 1 is negative 2, so there's my slope. My point is at 2, 0. My slope is negative 2. Let's do point slope form. Okay, good so far. All right, solve for y. Then final step, put in that decimal value. Okay, page 2. I think 2 is pretty easy. They already gave you all the data. Let's go to page 3. So just have a bit more variety here. So page 3. Okay, so your homework is going to be page 2 and 3. if you are working off of my classroom packet, just make sure that in your notebook that you're writing down the problem as well as your answer, just so that when I walk around and check, I can more easily see that you're working, that you're showing me the homework that I want to check. So, okay, so page 3, try number 5, see if you can work through this one on your own. Don't worry about the decimal. That's the last step. Focus on building your tangent line. Oh, sorry. We do have to pick an x value. So it says approximate f of 1.02. We always want to build a tangent line equation at a nice integer value. So what's a nice integer value that we can use to build our tangent line at 1? Yeah, so we always want to pick the closest integer value to whatever the decimal is trying to approximate. So you want to do this at x equals 1. So focus your attention on this first. Get your ordered pair, build your slope at 1, point slope form, and then you can worry about that 1.02 at the end of the problem. All you need is power rule to get to the derivative.
Did you say we get a calculator for this?
Mhm. Yeah, you get a calculator for this quiz.
But just leave it.
Yes, right. You can also leave your answer simplified, and I'll be okay with it too. Yeah, your calculator is probably going to be more used for when it comes to related rates, and there's some of these decimal values that you want to be able to plug in. So. All right, any questions with 5? All right, number 6, what x value do we want to use if we're trying to, yeah, so always pick the closest integer value to build your tangent line. 1 into the function will give us our y value, but to find the derivative, in this case, we got to go through what? Quotient rule, yeah. So you're going to build your derivative through quotient rule, then plug in the 1, and then get your slope. A little bit more work involved with number 6. Take a look at 7. I'll leave this up here if you're still working on 6. But for 7, same process here. What X value would you choose?
2.
2. And then this one, what rule would use to find the derivative? Chain. Okay. So find your ordered pair from the function, build your derivative using chain rule, plug 2 in, get your slope by slope form. Okay, after this, we're gonna see if we can finish up page 2. I think even after that, we may have a little bit of time, so I'll let you just start previewing into tomorrow's topic with related rates, since there's not a whole lot to do here. So in a minute, I'll switch up to number 7. And after this, we're just going to finish page 2, and then we'll be done with our homework. So we'll just do a little preview of the next section for tomorrow. Anyone have any questions for number 6? Okay, is anybody still working on number 6?
Do we know that, 1/8 and the 2/3 is equal to 1/4?
Oh, yeah, that's good. Yeah.
Squared.
Yeah, I'll talk about how, we can do that without a calculator. So 8 to the 2/3, maybe, I think students' inclination is want to deal with that 2 first, which will make it 64, and then we gotta do the cube root of 64, which is equal to 4, and that's fine, but, you don't have to do that, 2 first, you can do the 3 first. So I think that's the strategy here, is if you can make the number smaller first, then it doesn't feel that difficult to do without a calculator. But this is asking for the cube root, right? What's the cube root of 8? 2, and so 2 squared is equal to 4. And if you do it in that order, then it feels a lot more manageable. So here's another example. If I have 2, or sorry, if I have 32 raised to the is that right? Yeah. So if I have 32 raised to the 2/5, 32 squared, that's a big number. I think 5th root of that is difficult. But doing the 5th root of 32, that's more manageable, right? So the 5th root of 32 is going to be 2. And now 2 squared is equal to 4. 16 raised to the 5/4. Force the number small before you raise it up to a higher number. Okay, page 2. Let's see if we can get through this. This should be quick since all the slopes and order pairs were provided for you. And I check my math as well, since I didn't realize I had a key for this here. Great. Mhm.
Why would you multiply or? Never mind.
Okay. Yeah, let me know if you see something that's off.
Expression.
Yeah, go ahead. Check my work. And you guys get what I got? All right. Just need just to check my work. Okay, I think we have 10 minutes. Let me just do a head start into page 4. I mean, we're done with our homework, so we're just getting a little bit ahead. So page 4. That's completely small. All right, everybody okay? So related rates. Related rates are problems involving finding the rate of change for a variable with respect to time. So it's kind of similar to implicit in the sense that we're always going to attach a d over d or like a derivative variable to our y variable. But now we have a different independent variable. Now we have independent variable with respect to time. And because of that, now every variable is going to get that d over d, that derivative variable attached, not just going to be the y, every variable that we see. So this is another application for implicit. We're finding the derivative of variables with respect to time. Now, these problems are going to have a kind of word problem feel to it. A lot of this is going to be kind of something tangible that you can see and visualize. But let me just go down the steps. We don't have to do these steps in this order. In fact, a lot of times I do steps out of order, but these are all the things that we need to ultimately find in order to solve our problem. So we want to be able to read the problem and identify what's given to us. So we want to kind of associate the numbers that they give us into a variable that we're going to be using. And then we also want to write down what we're trying to find. We want to identify the variable that the problem is asking for us to solve for. And then we always are going to be starting off with some algebraic or geometric equation that relates the variables together. So it could be Pythagorean theorem, it could be the volume of a cube, it could be surface area of a cone, or surface area of a sphere. Once we have that starting equation, we're going to then build the derivative. But as we build the derivative, every variable is now going to have a d over dt attached to it. And then we're going to substitute and solve. Okay, this is an important note here that I will come back to over and over again, is remember that when the item or when the value is getting larger, you want that rate to be positive. When that value is getting smaller, you want the rate to be negative, regardless of direction. Sometimes we associate direction with a certain sign. Sometimes we associate right with positive, left with negative. That may not be the case. Okay, we need to kind of visualize what's happening to that value, that length, that dimension. Is it getting larger or smaller over time? Okay, so here's example 1. Oh, and by the way, there are formulas that you're going to have to know, but then there are also formulas that will be given to you. So the basic, I'll talk about them later, but the basic formulas like area of a square, area of a circle, circumference of a circle, we need to know those. But some of the more involved shape formulas like volume of a sphere, volume of a cone, okay, don't have to worry about those. Those will be provided for you. Same thing on the AP exam. Any three-dimensional geometric shapes, they will provide that for you. So you don't have to memorize those geometric, especially the three-dimensional formulas. Okay, so it says the size of a square are increasing at a rate of 5 centimeters per minute. How fast is the area increasing when the sides measure 15 centimeters in length? So ultimately, we're involving the area of a square. Okay, so that's the starting point. So we're going to build the area of a square first. So the area of a square is length times length, but I'm going to use x to represent the length of my area of my side length. Now this is what I like to do. As soon as I identify the equation, I like to go ahead and build the derivative. That way I get the calculus out of the way, and that way I can see all the variables that are in play for the problem. So we're going to find the derivative of a and x. So a is a to the first power, so a's derivative is just 1, right? But we need to attach a d over dt for that variable. So it's going to be dA over dt. So before, we would, like if it was y, we'll do dy over dx, right? But now it's going to be d of that variable over the derivative of time. Okay, so now time is going to be the one that's going to impact everything. So it's always going to be over dt. Okay, x squared, what's x squared's derivative? 2x. Before, we would leave 2x alone, but now x is no longer the independent variable. So we need to multiply this by what?
dx dt.
Good, dx over dt. The numerator is indicating what variable that you're working on, and the denominator is indicating the independent variable that is influencing the entire problem. So let me identify what these variables mean. So dA dt represents the rate of change. I'm going to just abbreviate rate of change with ROC. So rate of change of area with respect to time. We know x is the side length of a square, and dx dt is the rate of change of the length of the side length with respect to time. Okay, let's go back and reread the problem here. It says the sides of a square are increasing at a rate of 5 centimeters per minute. Any idea? What would you associate? What would you assign this value to be? Is one of these three variables here. Sides of a square are increasing at a rate of 5 centimeters per minute.
dx.
Good, dx dt. So the units also help a lot because you know that, okay, centimeters, that is going to be the unit for a length, but then it can't be x because there's a time component as well. So if I see a time component, it's got to be something over dt. We know it can be dA over dt because dA over dt would be talking about the area. So we know dx dt is going to be 5 centimeters per minute. The other thing that we know is that we see the word increasing. So increasing, that means this is getting larger. If it's getting larger, we know that the sign associated with it is going to be positive. Anytime the problem is giving you information about a rate, you have to be the one to decide whether you keep it positive or make it negative. And there's always going to be enough context clues to let you know whether that value is shrinking or is it growing as time passes. Okay, how fast is the area increasing when the side length is 15 centimeters in length? How fast is the area increasing? What are we looking for? But you see the word area increasing. So this is not area, this is not A, but it's what? dA over dt, right? So if you see the word increase, decrease, rate of change, if there's a unit, anything with time involved, it's got to be a d over dt. It can't be a static value. So you know dA dt is the variable that ultimately you're trying to solve for. Okay, when the sides measure 15 centimeters in length, what's 15 going to be associated with? X, yep, that's a static value. And now we just take everything and plug it in and solve for our missing variable. dA dt is the unknown. 2 times x, so 2 times 15. And then dx dt is 5. Ten times 15. We get 150. So the area is going to be increasing at this rate. That's our answer. And then units, okay? When we talk about units, look at the variable that are involved and then just identify the units for each of those variables. So area is in terms of what? What's the unit for area? Centimeters squared. Okay, what's the unit for time? Minutes. So that's it. Okay, so if you're ever struggling with a unit, look at your variables involved and then just put those variables that are in play and put them over each other. Okay, tomorrow I'll be checking pages 2 and 3. We did it all in class, so there was no homework. And then tomorrow we'll just focus on the rest of our notes for related rates. Guys, if you took one of my classroom copies, when you leave the class, just make sure you return it back to the front.
I mean, this one doesn't think that.
Get through it for like mistakes. So you want to go? After you find your like derivative.